Hi everyone. So today I'm going to do practice problems work the practice. I'm going to work the quiz for chapter 1 and chapter 2. So if we draw the following condensed structures and bond line formula, if we start with CH3, that's going to be the terminal carbon, CH2, CH2, CH3. So this is the proper bond line formula for this structure. Now, how I look at these is I think CH3 and then the next carbon it's going to be bonded to. It'll have one hydrogen, so one implied hydrogen, and then this OH here in parentheses, that indicates that, I'm going to try to get this camera a little closer for you. That OH indicates in parentheses that the carbon is bound to the hydrogen and also the oxygen and then another carbon. So this carbon is bound to an implied hydrogen, an oxygen, and then this carbon. This carbon has two hydrogens and then the final carbon. So usually the way the condensed structures are drawn is they have clues in them, is how I like to call it. So a carbon, is whatever comes after it will fill up the octet until the next carbon comes. So this carbon has three hydrogens, and then the final thing to fill the octet will be bonded to another carbon. And that carbon has a hydrogen and an oxygen that will fill the octet, so then it goes on to the next carbon. This carbon has two hydrogens, and then all it needs to fill the octet is the last hydrogen or the last carbon. And then this carbon needs three hydrogens because there's no carbon after it. So that's kind of the clues written into it. This one's a little different. Okay, so we know there's 1, 2, 3 carbons. So I'll start with that. 1, 2, 3 carbons. This carbon only has two hydrogens, and this carbon only has one. When that happens and there's nothing else that's going to fill up the octet, you can assume a double bond there. So if this carbon only has two hydrogens, if I drew out the Lewis structure, and the next carbon only has one hydrogen, and then you have CH3, well, there's no other functional groups indicated, there's no alcohols, nothing else that's going to fill it up, and both of these are short on their octet, well, that double bond would take care of filling up that octet. And then for D, we have CH3. So the hydrogens fill up its octet, except for the bond to the next carbon. That's filled up by 2. And then the CHO is shorthand for an aldehyde. You can draw this hydrogen or you don't have to. It can be implied, but sometimes people put it there just to be clear. And if you didn't already know that CHO is shorthand for the aldehyde, you could draw the carbon. If you did OH, that carbon is missing its octet. It only has one bond to it, so that doesn't make sense. So then your other option is to do carbon with a hydrogen and an oxygen bound to it, but it's still short its octet. So you'd have to find a way to fill in a double bond. And you can't fill in the double bond this way because this carbon does have a full octet. So a double bond there would give 5 bonds to that carbon. So the only place you can finish filling in the octet is that oxygen right there. But as you go through OChem, you'll start to notice that is an aldehyde, and then this indicates a carboxylic acid. And the reason they don't do COH is to distinguish this. This COH would indicate there's an alcohol there, right? But because the H comes first, that indicates the H is bonded to that hydrogen or that carbon. So that's part of it as well. Okay, the next question. Identify which is not a valid resonance structure in the box. Okay, so this negative charge indicates there's a lone pair there, because if you have a formal charge, if you're calculating formal charge on carbon, it starts with 4 valence electrons. 1, 2, 3 bonds are drawn. And then how would you get to a negative? 4 minus 3 equals 1, so you'll still need to subtract 2, so you assume that lone pair. So the negative on a carbon usually indicates a lone pair on the carbon. Now this lone pair, maybe I should draw these in different colors so you guys can kind of see where I'm coming from here. If this lone pair were to go here, there's already 1, 2, 3, and no charge, so an implied hydrogen down here. So you can't get a double bond down there. That won't work. So question 2 indicates that either you've lost this hydrogen, or with a negative charge, I guess the hydrogen is still there and it has 5 bonds to carbon, which doesn't work. So not valid because 5 bonds to carbon or moved hydrogen. Either one of those is correct. So that doesn't work. Now if we try to move this lone pair here, there's 5 bonds to this carbon right there, but one can break and end up like that. So that gives you a structure. If I drew it out, it would end up looking just like this. The lone pair that was here became this bond, and the bond that was here became this lone pair. So that is a valid Lewis structure. And then if you went the other way, if the lone pair came over to this side of the bond, this double bond would have to break because there's 5 bonds to carbon and become a lone pair on the hydrogen or on the nitrogen. So if we did that, the lone pair here becomes a bond right there. And then if we have our lone pair on the nitrogen right here, it would be negatively charged from what used to be the bond there. So this is also a valid Lewis structure. Now, if I'm starting from the strongest point of electron density, these are the only 3 places I could go. But there's one more Lewis structure. So the only way I could see this Lewis structure happening is if you take this lone pair and make a bond right there. But this already has 2 hydrogens on it to get a full octet. There's no charge on that carbon, so we're assuming 2 implied hydrogens. So for this nitrogen to go there, there would have to be 5 bonds to carbon. So that is not a valid Lewis structure or resonance structure. It would have 5 bonds to carbon, or they removed a hydrogen atom. So 1 and 2 are valid Lewis structures, or 1 and 3 are valid Lewis structures, 2 and 4 are not valid Lewis structures. This is the molecule serotonin, a neurotransmitter responsible for regulating all these different things. So you're supposed to circle the functional groups and write down their names. So right here I see an amine. There's no carbonyl or carbon double bonded to an oxygen nearby, so it's not an amide. I see another amine right here. And then I see right here, you could either break this down as an alcohol and an aromatic ring, but a more proper answer if you see these 2 together is actually phenol. So we gave credit for either of those answers. I think partial credit maybe for separating it out. And then if you look at this amine, it's bonded to 1 carbon, so it's primary. This amine is bonded to 2 carbons, so it is secondary. Now, it's like back and forth on whether or not alkenes are a functional group. But this is technically an alkene, which I'm not sure I would call it a functional group, but it is it is something you can notice. So I think we gave extra credit if you noted the alkene there. Okay, now this is the molecule chloroform. What is the hybridization of the central carbon atom? Well, if I'm doing a quick and dirty hybridization, I know that I would need 1, 2, 3, 4 different molecular orbitals, so it would require at least 1 s and 3 p's. So that's sp3. So sp1, p2, p3, sp3. So that's the right answers. That's how I usually get it for this, is I just counted up the different domains that it's bonded to. If something's sp3 hybridized, it's tetrahedral. And for each bond, okay, so chlorine is more electronegative than carbon. So we're going to draw the dipole moment pointing out and leave a positive charge behind. Here we'll draw the dipole moment pointing out and leave a positive charge behind. And here we'll draw the dipole moment pointing out and leave the positive charge behind. Carbon, just slightly, is more electronegative than hydrogen. So same thing there, we'd point towards the carbon. So that's the answer to that question. Is the overall molecule polar? Well, all of these are pointing this way, so I would say yes. The overall molecule is polar. What intermolecular forces would be present between the 2 chloroform molecules? Well, if you had 2 of these, they don't have hydrogen bonding because there's not a hydrogen bonded to oxygen, fluorine, or nitrogen. So not hydrogen bonding. They would have dipole-dipole because when they're coming near each other, there's a partial positive on one side of the molecule, partial negative on the other. If it comes into contact with another molecule that has that same thing, they could line up and have a strong attraction here between 2 molecules. And then all molecules have dispersion forces, which are temporary induced dipoles based on the molecule being polarized. Okay. So can you determine which peaks correspond to the functional group of carboxylic acid? This is a classic carboxylic acid peak. This is due to the OH here, but also any of the sp3 hybridized hydrogens will come down here. And then this right here is carbon double bonded oxygen. So that is the answer to this quiz. I hope that was helpful for you. And please let me know if you have any questions.